Good morning. All right, so day 2 of our exponential growth decay. So I'm going to go through some examples real quick with you, and then I'm going to do some actual work with you so that we can get the hang of this a little better. First things first, I forgot to go over scientific notation. Again, I made some assumptions. They were obviously wrong. So let's just go through a brief little intro real quick on scientific notation. The rule with scientific notation is that represent small or large numbers as numbers between 1 and 9. So, and then it uses exponents. You'll see it's really simple way to do this. All right, you got to know that when you don't see the decimal point on a whole number, you know that it's always at the end there. It's at the end right there. This is a very small number, hence you see the decimal point, so it's really, really small. So here's how this works. You need to represent this huge number, 350,350,000, into a number that is between 1 and 9. What's the purpose of this? Just to help expedite, like in astronomy, or again, speaking with just large numbers of distance, travel distance in space and whatnot. Nonetheless, you got to know how to do this. So here's how you do it. So I'm going to put my decimal point right here between my 3 and my 5. So this is 3.5, and you have to include all non-zero numbers. So this 0 stays because it's a placeholder. 0, 3, 5 times 10 to the, if it's right here, how many times did I move it to get back over here? So just count. 1, 2, 3, 4, 5, 6, 7, 8. That's to the power of 8, just like that. And then right over here, same thing. I include all non-zero numbers. That's crucial for this. So I know I'm going to put the decimal point right there between the 2 and the 6. So 2.69 times 10 to the, let's count. If I put it here, I got to move it back over here. Just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. Now, how do I do it with these really small numbers? Again, I got to move this decimal point right here between the 5 and the 6 so that it's represented as a number between 1 and 9. So, to do that, I just do 5.652 times 10 to the... Now, here's the difference. When I'm representing these small numbers in scientific notation, my exponent is going to be negative because I have to move this decimal point back to the left. How many times? 1, 2, 3, 4, 5. So this is a negative 5 because it's going back to the left 5. Same with this one. Include all non-zero numbers. 3.052 times 10 to the, let's see, 1, 2, 3, 4. Negative 4. And that's your quick little intro on how to do some scientific notation that I know I forgot to go over yesterday. So moving on, I got some examples on the right of exponential growth equations and exponential decay situations. So let's check this out. Okay. Notice for growth, the stark difference is our growth factor, the number that's in our parentheses. Because remember, the format of a exponential growth is y equals a times b to the power of x. Remember, this is your growth or decay factor, and this is your initial value. And this is just a repeat of yesterday. Initial value or Y intercept. Okay? Notice how the growth, every single growth situation, our growth factor is always greater than 1. Greater than 1, greater than 1, greater than 1. Okay? My Y intercept, or my initial value for this, is 2, 3, and I see an invisible 1 right there. Okay? Now, decay examples. Here's how this works for the decay examples. Every single decay factor is less than 1, but they're never going to be negative, ever. Okay? So right now, we got this, 0.95, 0.15, and 0.5. Back in a second with some more examples. Hello again. All right, here we go. So one more thing before I forget, you guys, we'll get into this during class, and then I'll have a whole separate lesson about percentages, just so this makes sense. But you guys got to know that whenever these are all percentages that were changed into decimals, okay? Because you always change percentages to decimals when converting into growth or decay factors. So like for instance, forget the 1 right now. If this was a 0.75, that's a 75% increase. So it's one, you always add 1 to the decimal. So it's 1.75. This 0.05 is 5% as a decimal. So then that's really 1.05. And again, you just always add 1. Well, in this case, you're going to have 2 point, and I'll get into what this means at another point. But again, 0.5 is 50%, and this is actually 150% because that's how we got the 2 right there. Over here, as a decimal, this is 0.9, I'm sorry, as a decimal it's 0.95, but as a percentage that would be a 5% decrease, okay? Because you do 5%, you ever take the 5% and minus it from the 1 instead of adding it to the 1. So in this case, you got 0.15, that's 15%, so the opposite of that is 85. So that means this decimal of depreciation or of decay is 85% lost. And again, we'll go into this in depth at another point, but I want to make sure you guys understand that in case you see some stuff today. Now, right now, what I'm doing here is I got 2 different graphs, and we're going to make exponential equations based off these graphs. And it's a lot very similar to making equations from tables, because at the end of the day, I have some points on my graphs that I can easily identify, and all I have to do is create a table in order to make the equation, okay? So each one, I identify the points for you, but you guys will see like where the graph crosses the 4 corners of the graph paper. You'll be able to see exactly what's going on there. Okay, I'll erase this in just a minute. So I got one point here at 0, 5. I got another point here at 2, 8. And I got another point over here at 3, 16. All right. So that said, you know what? I think I got some other better points to make this easier. Hold on. I got this at 1, 8. I knew I made a mistake. This is 1, 8. This is 1, 8. And this is going to be 2, 16. That's what I thought I made a mistake. This is 2, 16. That's what I thought it was. All right. So coming back. There we go. So this is 1, 8, and this is 2, 16. All right. So on and so forth. Here we go. Here's how you do this. I don't know what I'm multiplying by to get from this to the other. All right. Is that 0, 5? Did I make another mistake? Huh. That's 4. This should have been 0, 4. Should have been right here. I knew I made a mistake doing this last minute stuff. All right. So there it is. This point is 0, 4. My apologies. This is 0, 4. All right. So first things first, I can know my equation because the standard format is y equals a times b to the power of x. And my a is my y-intercept, and my y-intercept is explicitly told to me, so this is y equals, let me get this up for you guys so I can see you. Perfect. All right, y equals 4 times, well, what's happening every single time? It's multiplying by 2. So my 2 goes right here to the power of x. That's how it's constantly changing, okay? And this is represented as a growth factor because it goes up and to the right. Just like a positive linear equation, lines go up and to the right, okay? Now, there's no negative factors, all right? There's all the decay factors, and decay factors are numbers that are between 0 and 1, all right? So on the same sense, I'm going to erase some of this. So I got my x and my y right here. I got my 0 and my 2. I got my -1 and my 4. I got my -2 and my 8. And I got my -3 and my 16. Okay. So again, process will always be the same. All right. So first things first, I have to find my y-intercept, and it's pretty much told me right there. So this is y equals 2 parentheses. Again, my growth factor is multiplying by 2. So this is 2. I'm sorry. So it's not, because it's going from -1 to -2. Hold on a second, what did I do wrong? All right, so to help you guys understand the mistake that I made, which is a mistake that I'm sure lots of you can make, the reason that I caught my mistake, and I'm like, wait a second, this is not right, because my growth factor, this is a growth factor, this is greater than 1. My graph goes up and to the left, therefore this has to be a decay, so this has to be something between 0 and 1. So here's where I made my mistake. we read this graph, we laid down the points left to right, and the math that we did to get from one point to the next was multiplying by 2. You have to follow the same rules. If I'm writing them down left to right, I always write them down left to right. So I got to get my points going from order from left to right. So what I should have done instead was this, okay? I should have started off at the top, just for the sake of my math, to be -3, 16, -2, 8, -1, 4, and 0, 2. Now, I'm still looking at multiplying because we never divide within this concept, okay? So now, instead of dividing by 2, we are multiplying by 1/2, multiplying by 1/2, and multiplying by 1/2. So our decay factor in here should have been 2 times 1/2 to the power of x, all right? So you saw that I made a mistake, and I caught my mistake because I know by the shape of this graph, this number has to be between 0 and 1. Therefore, I was able to catch my mistake and see what I did wrong there. So again, the rules to follow. If you write them down left to right, always write them down left to right in order so that you can see the correct way to go. All right, I'll see you guys in class, and this will hopefully make a lot more sense then.